Injector control pressure is a key concept within fuel injection systems, playing a pivotal role in optimizing engine performance, improving fuel efficiency, and reducing emissions. This is especially vital in internal combustion engines, where precise fuel delivery impacts everyday driving and aligns with automotive technology trends. The focus here is to break down this technical aspect for a general audience, assuming a high school reading level, while maintaining depth suitable for an expert with over 20 years of experience in fuel systems. Injector control pressure, often abbreviated as ICP, refers to the pressure of the fuel as it is delivered to the injectors in a fuel injection system. This pressure directly influences the amount of fuel sprayed into the engine's combustion chamber for each injection event. The higher the pressure, the more fuel is delivered for a given duration that the injector is open, and vice versa. Research indicates that ICP is particularly critical in diesel engines. These engines require high injection pressures, often in the range of thousands of pounds per square inch, to atomize the fuel properly and ensure it mixes well with air for efficient combustion. Diesel engines rely on precise pressure ratings and high temperatures to generate power, unlike gasoline engines that use a spark for ignition. The concept is similar in gasoline engines but varies by system type. Gasoline direct injection systems, which are increasingly common, operate at high pressures, typically around a few hundred psi. Older port fuel injection systems, however, operate at much lower pressures, around 30-90 psi. An unexpected detail is that, while injector control pressure is commonly used for diesel engines, gasoline engines more frequently use the term rail pressure. However, the underlying principle, the pressure of the fuel supply to the injectors, remains consistent across both, affecting fuel delivery accuracy. The significance of maintaining the correct ICP cannot be overstated, as it impacts several critical factors. The right ICP ensures the engine receives the precise amount of fuel needed for optimal power output. Too low or too high pressure can lead to misfires, reduced power, or even engine damage. For example, a P291 code indicates that ICP is too low, potentially causing performance issues. By controlling the amount of fuel injected, the engine can operate at its most efficient fuel-to-air ratio, maximizing miles per gallon. This is crucial for reducing fuel consumption. Roper fuel atomization and combustion, facilitated by correct ICP, help reduce harmful exhaust emissions like nitrogen oxides, particulate matter, and hydrocarbons. In diesel engines, high ICP ensures fuel is well atomized, reducing soot and NOx. In gasoline engines, correct pressure minimizes unburned hydrocarbons. Consistent and accurate fuel delivery minimizes wear and tear on engine components, prolonging the engine's life. This is particularly important in high-pressure systems where components are under significant stress. To illustrate, consider an analogy. ICP is like the water pressure in a shower head. Higher pressure means a stronger flow, just as higher ICP delivers more fuel. A slight miscalculation, like incorrect water pressure affecting your shower, can significantly alter engine behavior, akin to how air pressure affects an airplane's flight. In modern vehicles, the management of ICP is largely automated, with the engine control unit playing a central role. The ECU uses a pressure sensor to measure the current ICP and adjusts the fuel pump's output or other components to maintain the desired pressure. In diesel engines, the high-pressure fuel pump is often controlled by varying the timing or stroke length to achieve the required pressure. In gasoline engines, the fuel pump, typically electric, has its speed or duty cycle adjusted. Maintenance and troubleshooting are key practical applications. Regular inspections and replacements of fuel system components, such as filters, pumps, and injectors, are essential to prevent issues. For example, clogged fuel filters can affect pressure, leading to performance problems. If there's an issue, the vehicle's onboard diagnostic system might illuminate a check engine light and store a trouble code. For performance enthusiasts, increasing ICP can lead to more power, but this requires caution. Higher pressure can stress fuel system components and the engine, potentially causing damage if not managed properly. CP is measured using pressure sensors, with the ECU adjusting the system based on real-time data. In some vehicles, especially older models, mechanics might manually check fuel pressure using diagnostic tools. But in modern vehicles, this is mostly electronic. Adjustment can involve tuning the fuel pump or replacing components like the pressure regulator. In maintenance, ensuring the fuel system is free of leaks and clogs is vital, with regular checks recommended every 30,000 miles or as per manufacturer guidelines. In conclusion, injector control pressure is a cornerstone of modern fuel injection systems and is critical for engine performance, efficiency, and longevity. It ensures accurate fuel delivery, impacts emissions, and supports engine durability, essential for everyday driving and automotive advancements. Looking forward, as automotive technology evolves, with a focus on electrification and stricter emission regulations, precise fuel pressure control will remain paramount. Future engines, including those in electric vehicles with range extenders or hybrid systems, may still rely on similar principles, adapting ICP management for new fuel delivery technologies.